Hey everyone, dear friends, dear community members, C++ developers, ladies and gentlemen, welcome to our meetup. Thanks for being with us
Welcome.
today. Hello, my name is Necati Ergin and I'm your host. I'm the founder of the C++ Turkish community. I have been teaching C++ for 20 years and I've been using C++ since 1993. As you guys all know, our guest today is Mr. Bjarne Stroustrup. He doesn't need much introduction for most of you. He's a distinguished computer scientist. He's the inventor, creator, designer, and the first implementer of C++ language. He has also he's also the author of the books, the C++ programming language, a tour of C++, programming principles, and practice using C++. Hello, Bjarne.
Hello.
Back in 2001, Bjarne was in Istanbul, Turkey to give a seminar at the Technical University of Istanbul, and I had the chance to attend it. I want to show you some pics here. Okay, it was 20 years ago.
Yeah.
These pictures were taken in 2001. Now, after 20 years, I'm really delighted to host him in our meeting. I'm joined today by my co-host Doğukan Yiğit Polat. Hi, Doğukan.
Hi. I'm Doğukan, and I'm actually currently in Singapore, as Necati Hoca said, and I'm doing PhD here, and I'm working on neuromorphic computing systems, and I'm trying to use C++ both in my research and in my recreational programming projects, and I'm in the community for quite a few years, and yeah, that's all about me.
Doğukan is in Singapore, I'm in Istanbul, Turkey, and Bjarne is in New York. So, what is our program today? First, Bjarne is going to talk about good C++ code briefly, and then there will be a Q&A session. We have already collected some questions from our community members, and we're going to pose these questions to Bjarne. Dear audience, I don't want to take much of your valuable time. Now, please join me in welcoming our very special guest. Welcome, Bjarne.
Welcome. Thank you for joining.
Good
I'm
to be
super
here.
excited to having you on. It was very nice of you to accept our invitation. On behalf of the Turkish C++ community, C++ developers, and all C++ lovers, I would like to express our gratitude to you. We are very grateful to you for inventing C++ and your everlasting, invaluable contributions to it.
Thank you very much.
Okay, Doğukan,
So,
then we can leave the stage to Bjarne.
Yes, we should leave the stage, and let me put on the slides for you, Bjarne.
Yeah, please. Okay, so I wanted to say a couple of words before we went into the Q&A, just to put sort of the big picture in place. And basically, the reason I work with languages with C++ is that I like to see nice applications to be done. I want to see useful things built. And I think the way I value a programming language is what you can do with it, what the quality of the applications. I spent less time on obscure language details, more trying to figure out what it is you have to do, and then you go to the details. So here's some examples of that. Could we see the next slide?
Sure.
So basically, C++ rests on two pillars, what probably know. But basically, there's a direct map to hardware. If you want to squeeze out the last cycle and the last byte, you can do it. You don't have to do it all the time, but when you need to, you need to. And that includes unusual hardware like signal processors, GPUs, FPGAs, and such. If you really need performance, you can dig down well below where we usually think of computing as going and optimize the key bits. And of course, down there, deep in the hardware, deep in the unusual hardware, is not a very pleasant place to be for a programmer. All the errors are could be disastrous. All the help is inferior, and so you need to lift away from that into something that's more fit for humans, and that's where the abstraction mechanisms comes in. And lots of languages had extraction mechanisms when I started, and lots have today. But still, my focus was not to lose the performance as you went up the abstraction levels, getting towards zero overhead abstraction, not just when you're debugging, but when you're actually deploying the stuff wherever you are deploying it. So abstraction has to be affordable. Could I get the next slide?
Sure.
And basically, a language doesn't just spring perfectly out of a designer's head. It relies on feedback to figure out what are the right problems to solve and what are the techniques that work for solving them. So C++ was basically, from the beginning, designed to evolve, to change over time, and having those decisions guided by real use. So as an engineer, Archimedes, and that's the machine there in the middle that builds all the high-end chips. Basically, if you've ever used a high-performance chip, you rely on the C++ program that controls that. And up at the top there is one of my favorites, which is the Mars copter that's whizzing up along on Mars. It was supposed to last for maybe 5 flights, and it did 20 some last time I checked. Good engineering, good software. Next slide. And so over the years, C++ did evolve as it was planned to do. C with classes was a relatively simple thing. We had classes, functions with function argument checking. We had constructors and destructors, which is the basis of everything in C++, and coroutines, which was my bread and butter for 10 years. And then it evolved over the years, and more people came on board, and we got more features to serve a wider range of users. And with C++ 20, we actually got coroutines back, finally. Finally managed to convince people that they really work great. And it's still growing. The dotted line up there is actually real. It's not conjecture, it's measured number of users. Anyway, next slide.
Sure.
And basically, a lot of what C++ is used for is foundational. We don't see it. It's like the bits and pieces of an engine of a car. We do not want to see them. We do not want to have to know about how the engine works. And so in the same way, people tend to forget that C++ is there because it's everywhere. You like to write, say, JavaScript. What do you think the JavaScript engine is written in? Java? Yeah. All these modern languages, what do they use for their techniques? LLVM, that's C++. You do AI, that's TensorFlow and things like that. Anyway, so I've done enough to set the big picture, and we can now get into details and detailed questions. Thank you.
Yeah, thank you very much for sharing our thoughts on where we see C++, where we can see it, where we can use it. So now we can move forward with our Q&A session. And Necati Hoca is going to start with his question.
Thank you very much. In 2015, you initiated C++ core guidelines, and you still lead it today. Starting with the book Effective C++ by Scott Meyers, and later on, the book C++ Coding Standards by Sutter and Alexandrescu, there have been several approaches to defining and documenting good C++ code. There are a number of styling guides or coding standards like Upsail, LLVM, GNU, Chromium, Firefox, etc. There are also Safe C++ guidelines like MISRA, AutoSAR, and GSF. As there are a number of different guidelines and coding standards, almost unavoidably, there are incompatibilities and or contradictions among them. What's your take on it? How do you think they should be handled? Can we think that C++ core guidelines is a template and other style guidelines are partial specializations of it? Thank you.
If you have a general purpose language, and especially if you have an older general purpose language, it can do lots of things. And that is essential because people work with people that do different things. But it gets big. Also, when it gets old, some things that used to be necessary or good cease to be so because we get better facilities. Difficult things get hidden inside libraries, etc. So there are always a need for guidelines or coding rules or something like that. And by and large, we hate coding rules because it stops us from doing exactly what we want. But it's necessary for collaboration between people, and it is necessary for getting people up to speed with modern things. So this goes back way before me. The core guidelines has its roots in some of the work I did actually for the Lockheed Martin for the flight software for the Joint Strike Fighters. There's a standard called JSF++ that's used for that. That was, to a large extent, my handiwork together with some aerospace engineers. And then some of it was in the advice sections of a book I wrote, the C++, a tour of C++. And then I worked together with other people, including Herb Sauter, including somebody from Red Hat, Google, Facebook, lots of people involved in the C++ core guidelines project. You mentioned Scott Myers. He was not part of that. And anyway, we need not just a set of guidelines, because very often guidelines are written to stop bad programmers writing bad code. We wanted something that gave a guideline, a framework for good programmers writing good code. There's very few rules in the core guideline that says you shouldn't do that. If it does, it says you shouldn't do that, you should do this instead. It is not useful just to tell people not to do something. You have to tell them what is a better way. And the core guidelines are being maintained. Another problem with guidelines is that they get written and then they sit there and they don't get maintained, and then they get very old. And so we work on that. We try to make guidelines that makes code less error prone, easier to write, and still run as fast as ever. It's built on the principle of a subset of a superset. First, we superset the language using libraries, and then we subset, saying that the facilities that was necessary to build those libraries shouldn't be in application code. So for instance, new and delete belongs in resource handlers. So we provide the resource handlers, and there's a rule says don't have naked news and naked deletes outside these handlers, because that's where you get the memory faults and such. We don't like memory faults, so we avoid them. And then the whole thing is designed to be supported with static analysis so that you can actually provide guarantees. I want completely type-safe C++, and we're getting it. And we're doing that without a garbage collector because one of the techniques is not to generate any garbage. Things like that. So it's a principled framework, and yeah, we're still working on it.
So I have some other question for you, Bjarne. Thank you for your answer. It was a very detailed one. So my question is a little bit more specific, but a shorter one. So in C++, we have tons of different tools for handling errors, and error handling becomes, especially for beginners of the language, becomes too convoluted. What are we going to use for it? Are we going to return an error code? Are we going to return a struct that contains the error code and the actual return value? Or are we going to return an optional? Are we going to throw an exception? So which of these mechanisms should we teach beginners of the language?
Yeah, I think we should keep it simple. The problem is that just so many people try and find a much better and therefore very different way of doing error handling. And so they say we have N ways of doing error handling. It's far too many. Let's solve this problem. Let's add another one. And of course, the old ones don't go away. I think we need roughly two. For errors that propagate up the core chain, that is, errors that can't be handled locally, we need exceptions. Otherwise, people forget to handle the errors. They look at errors all the time. Code get littered with if then else's or other things like that basically to percolate the error up till you get to someone who has a sufficiently global view to decide what to do about this error.
Yes.
There's a lot of those memory management problems, or exhaustion and such are examples, but also network handling and I/O stuff. There's a lot of them. And then there's a lot of things that can be handled either very locally or just at the next call up. Things like if I open a file, I should jolly well expect it to not open properly, and I should have a test in the in where I open that file. And there's a lot of those, and then you have to decide on an error handling strategy. You have to handle errors that can be handled locally and can be reasonably expected. You have to handle them locally. An if statement will do fine. We have the problem of how to percolate them. Just one level up, I think a return value is the right thing. Quite often, a pair of values is the right way. The correct error plus an error, a thing that says, sorry, the correct value plus one that says if it wasn't the correct value. And you can do that in a variety of ways. I see a claim about expected on my screen, but it's one about 10 that people are using, and that's a problem. But there should be about two.
I see. Thank you very much for your explanation.
Oh,
in your presentation,
maybe before we go further, I should show you something. I'm sitting here in my study, and I just finished this thing here.
Oh, great!
It's the
a third edition of a tool.
Third edition, yeah.
And
as a matter of fact, that was one of my questions.
Okay, sorry to answer it, but
no problem.
It is that there's a section about error handling in this one, which actually gives a fairly detailed version of the answer. I mean, this is an interview, so I have to do some arm waving because we don't have time for anything else. If you want a more solid answer, this is the one. This is the third edition. I mean, not that the second was bad, but this one is up to C++ 20. And the main value of this book is that it's relatively thin.
Bjarne,
Yes.
by the way, is there any new edition for C++ programming language, a fifth edition, including C++ 17, 20, maybe 23?
I'm
Are
not
you
I'm not working on it.
okay?
It would take me 2 years of solid work to do, and it would be very thick. I'm not sure that that is the right thing to to work on. There's so much stuff about the new features and the detailed new features, and so much excitement about them that gathering them into a big solid textbook is not what people expect. So I'm working on the overview thing, which is that book I just showed you there. It just came out last month, and it has C++20 in it, so it does that. And the other thing I'm thinking about is teaching material. People do need a textbook to learn how to write programming
Yes.
from scratch. Otherwise, they'd say, "Oh, just give me the syntax, and I can write in any language." Yeah, you can write bad code in any language without any systematic teaching. So those are the two things I'm thinking about. I'm thinking about the overview for people who are already programmers to bring them up to C++20, which was the book I showed you, and then the textbook, which is I think it's still all right, even though it's C++14. But I'm thinking about modifying that. But the massive book of everything, maybe the time has passed from that kind of book.
Okay. In your presentation, you said that the value of a programming language is in the quality of its applications. Are there any applications or uses of C++ that you've been especially excited about?
I think I
Mars
just
rover
answered.
or something?
I think I just answered that one, didn't I? With pictures. Yeah, I like the scientific engineering applications. These are things like rockets and spaceships and Mars rovers and
Mars rover.
helicopters. But then you go back down to Earth. If you buy a modern car, it's probably C++. And that's one reason I'm very interested in reliability and things like that. When I press the brake on a car, I really want it to stop. And that's software, and it's usually good software. Also in scientific things, there's CERN with the high energy physics research, finding new particles and such. It's very exciting. But it's C++ is basically everywhere, and so you look and you think, wow, I had tiny little contribution to this. I mean, we're talking here. We have one guy in New York, one guy in Singapore, and one guy in Istanbul. How did that go along? There's C++ in the computers, in the video equipment, in the capture, in the transmission, in browsers, and it's everywhere. But the things
Also,
that I
probably
really
in the
like,
hardware.
yeah, James Webb Telescope. Somebody pointed out this is C++.
Yeah.
We have C on L2, and there's people who make strange noises about C++ not being reliable. Wait a minute,
Oh.
it's on Mars. There's no repairman there. At the L2, there's no service station up there. It has to be good. It has to be really good hardware software. What people don't seem to understand is it's a difference between foundational software and sort of control software for high-end gadgets, and then a web browser or a web app. It's not the same kind of code. I think there should be different education for people doing different kinds of software. And sometimes people don't seem to understand that there are many, many different kinds of software. I'm mostly interested in the engineering applications.
Yeah, I also agree that the infrastructure that hosts the applications is another art than creating the applications themselves. So they're obviously going to be written by people with different expertise, and they're going to require different language. I agree on that. So should we move on to the next question? Do you have anything else to add?
Let's see what else there is.
Okay. So let me go on with my next question. For this question is about the incomplete additions to the standard. So, for example, we now have the very amazing libraries such as std format and std ranges in the standard. But unfortunately, a lot of very useful features of these weren't included in the standard in full, especially in C++20. And because of this, I see a lot of projects and a lot of programmers around there using the non-standard libraries that are predecessors of these predecessors of the ones that are in the standard. So what is the reason for this? Like, is it intentional, or is it because we don't have time to release the thing in full?
Doğukan, with your permission, I want to add something to your question.
Yes.
Also, for core syntax, when constexpr first added to the language, it was really very restrictive. And with each standard, now the restrictions are removed. Finally, we can almost make everything constexpr. Why in the very beginning it has been added in full as complete, but we have to wait for the other standards to add the other features?
Let me answer Igit's questions first and then come to the context afterwards. It is intentional and unavoidable because we don't have the time.
Mm-hmm.
Back in previous millennium, all standards came out either 5 or typically 10 years apart. And that was not viable, especially because once you got towards the end of a 10-year period, ready to get the new standard out, everybody says, oh, I must get my feature in. It has to get in now. Otherwise, I have to wait 10, 12 years. And so you started slipping from the 10-year schedule to something even longer. So some of us decided this couldn't go on. And Herb Sauter in particular came up with the idea of using a train model. The train leaves at its given time, and if you're not on that train, you get on to the next one. And so we started discussing how frequently can the trains leave. And I argued for 3 years as being the shortest you can do an international standard. There's a lot of work to get into a national standard. It's very hard to get things out if you put something wrong in again. It has to go through several levels of approval, including votes on at the national level. We usually get 21 or 22 to 0. We're good at this, but doing it in less than 3 years is very hard. So the train leaves the station every 3 years. We delivered 11, and we were sad that we couldn't do that sooner. And then we changed to the 3-year model. So we got 14, 17, 20, and by God, we're going to get 23 on time. But with this model, you don't have time to get a whole brand novel feature in. So you get what you can in and you leave the rest. But there's one more reason for these incomplete features, and that's that idea of feedback in engineering. We generally don't know how all the little details and how the more advanced features actually work out in the real world. There's fashions, and everybody knows, oh, the latest and greatest will work. Yeah, quite often it doesn't. So you have to deploy something and see how it works in the context of the rest of the language, in the context of the libraries, in the standard library, in other people's libraries, in the build systems, in the tool chains, and then see what happens and then fix it. The classic, there are several classical examples of that. The modern coroutines are very good, but they don't have sufficient library support. Quite often, you do the language feature first with a little bit of library support, and then you build the library support out later, because it's really hard to test some libraries without the language support.
So can we say that it is? Oh, sorry.
Then
can we say that? Okay.
Sorry. No,
you should go on. Okay. So can we say that it is growing in an evolutionary way?
Yes.
Taking
very
feedback from the
deliberately
environment.
so.
I see.
Yes, it's an evolving language. It relies on feedback, and that was clear from day one. Where it was just me, and I realized there's just no way I could build a sufficiently good and sufficiently comprehensive general purpose language. I need feedback, I need time. But anyway, let's get back to the context. There's another effect, is that when something is new and interesting, people don't like it. It's weird, it's useless, it's too expensive, it can't be done. So context was one of the features that had the greatest amount of opposition in the standards committee. It was loudly deemed useless and unimplementable. So we have to start rather conservatively with that. We being me and Gavidas Reis, designed and implemented it before we brought it to the standards committee. Not implemented it for all the little details in the standard language, but enough to demonstrate that the techniques would work. And we had absolutely no doubt this was useful. People write all of these macros and get into trouble with them, and it costs so much to compile macro-based code. So we had to do something better. It also gives us a version of pure functions because there's no side effects and no objects to read outside the parameters and all of these kinds of good things. It's a really nice practical feature. But boy, it was difficult to get it in. So it started very restrictively, and then we slowly released it. With more features, which we had actually mostly designed before we got it into the language, but it took years. These days, I worry more about overuse about context for functions than I do with underuse. We have succeeded in getting them on board, and of course, everything that is new will get overused and misused. But if you look at context for functions, compile time evaluation of fairly advanced functions, this is not just integers and floating points. It's also types. And now it becomes the backbone of concepts, which is the backbone of modern generic programming, which we finally got in. Again, me and Gavidas Reis, and also Andrew Sutton. So that's actually, I wouldn't say there was a plan, but there was a set of related ideas that we worked on to get this. And actually, one of the libraries we built while we were doing these ideas to do better static analysis became the backbone of modules. because there you need to represent and analyze source code. These things are related.
I see. Thank you very much for your answer. Nejati Hoja is muted, so I'm going to unmute him. I cannot unmute him.
Okay, sorry.
Okay.
Another question. Significantly, many C++ programmers think that the language has been lacking a nice type erasure mechanism for a very long time. Do you agree with these people? Are there promising proposals for language-level type erasure support? After the introduction of concepts into the language, is it now viable to have such a language feature that automatically creates polymorphic type erasing interfaces from concepts that fit certain criteria? What is the best way to achieve runtime polymorphism in today's C++?
I'm not a great fan of type erasure. Even the name is pompous. I like to see the types at least most of the time, and I do certainly not want an object to change types as it goes along. Yes, we can have a variant, which is good, and it has some uses. And we still have all the object-oriented stuff that works rather well for runtime polymorphism. Yeah, this is not a direction that I'm very keen on going. I'm very keen on the concepts which allows us to have interfaces that are far more general than plain old types, and as you point out, related to this type erasure question. But there's no type erasure. It's just it just deduces what the types are and uses them appropriately. If you think about it this way, a type specifies what you can do with an object and how it's laid out in memory, where a concept specifies what you can do to an object and doesn't say anything about how it's laid down in memory, because that's what has been specified with the type that match the concept. So you don't have to do it. It's far more general. You can write much better interfaces that way.
Thank you for your answer. But I still didn't understand the best way to achieve runtime polymorphism in C++. So do you think that defining virtual functions is a good way to go? If not,
it is often a good way to go if you want runtime polymorphism. There is no, I mean, you can't just say this feature solves everything. It has served well for 40 years or thereabouts, and it still serves well in many, many cases and many, many advanced applications. And I use a lot of static polymorphism, which doesn't need it and is often more efficient and better type checked, easier to manage. You don't have memory management problems there. But I don't see a desperate need of more kinds of polymorphism once you've got the basic variant. In C++ 17, we got variant, any, and optional, and they messed up the interface design so that the three classes have rather different interfaces, which is not good. They could have been basically unified. And in the kind of code I write, almost all variants, I don't use optional much, and I don't use any because I really like types. I don't want any I never saw anything that could be anything except deep in implementations of other abstractions.
Yeah.
Same reason we don't have a universal base class, by the way. Same
I
philosophy.
see. Yeah, thank you very much for your answer. So can I move on with the new question?
Sure.
Okay. So this was the previous one. So I just today I watched a talk by Jason Turner, and the title was "The Right Way to Write C++ Code in 2022." Just a very similar title to our talk today. He suggested using static and dynamic analysis tools as extensively as possible, which I agree, in the deployment pipeline. However, he also suggested shipping the binaries with hardening enabled. And I'm not very sure about that. Do you think that it is really necessary in a healthy C++ deployment pipeline to ship with hardening enabled?
Now, I didn't see that talk, unfortunately. Jason's talks are usually well worth seeing. So my answer is going to be somewhat incomplete. But I'm a great fan of static analysis, and it's an integral part of the C++ core guidelines. And many of the rules of the core guidelines can be validated either in Clang-Tidy or even better, actually, in Visual Studio's static analyzer. And that's what I think most about. For things to do with concurrency in particular, and when you have old code that you can't verify with core guidelines or anything else for that matter, you need to use some dynamic analysis. Now, whether you should ship with hardening or not depends critically on what it is you're doing. I would prefer to ship things that were designed well, was tested well, was statically verified to have the absence of certain problems like dangling pointers. I would definitely aim for shipping them without hardening. Now, if I had to use all kinds of libraries that didn't get that kind of heavy engineering testing, I would definitely think about hardening. But then exactly what is hardening? What degree of hardening is there? I did my PhD on a machine where you couldn't have memory errors because it was there was hardware support for that. That's actually my ideal. So we won't get there any day soon.
I see. Yeah. Thank you very much for your thoughts. So
Okay.
I guess I should say one thing more.
Okay.
I emphasized that there was many different kinds of programming, many different kinds of applications, and there's many different degrees of hardening and security and reliability demands, and people tend to forget that. And we wouldn't apply the kind of checking and testing needed on a $1 billion application at L2 to the latest little app, right? Remember, there's different things here, and we all have our specialities and our interests. I don't claim to be an expert on everything. Remember to test your requirements. Think of your requirements before you make statements about what needs to be done.
Okay, thank you. Another question, was there any C++ feature or library component that became a part of the C++ standard that you didn't support or raised concerns for you? Vice versa, Was there any proposal you supported or contributed to that was rejected by the committee? There were several proposals for unified function call syntax, and you also submitted one with Herb Sutter in 2016. That proposal was rejected by the committee. Do you think there is still chance for unified function call syntax in the future standards? That's the question.
So for the first part of the question, I am not going to mention any features I didn't want in the language so as to protect the guilty. On the other hand, I don't think there's any major features in the language that I would strongly oppose. There's lots of things and details that I would have liked and didn't get. The obvious example is the one you had there, unified function call, which I think we should have had. And I think it was a bit of a tragedy that it didn't come in. And I thought that the arguments against it were wholly insufficient. But then they thought my arguments for were wholly insufficient. So that's the problem. You have a large committee. You have 350, 400 people on the committee. 150, 250 turns up at meetings, and you need to get agreement. Agreement is very, very important. You need continuity. You need to try and minimize dialects. And so, yeah, I take my lumps, and sometimes I come back again. And it is by no means inconceivable that I come up with yet another proposal for unified function call. The problem here, however, is that the last couple of proposals were about as good as we could make them, demonstratively so.
Thank you. Okay, Yiğit.
Thank you, Bjarne. I have a similar question, kind of, not very exactly similar, but my question is on lessons learned. So as an inventor of this language that is arguably the world's most impactful programming language, do you have any suggestions for people who are interested in creating programming languages? More specifically, did you learn any lessons that you find particularly significant in the language design as you observed C++ from its birth all the way it progressively evolved into what it is today? In the past, I remember you were mentioning several things such as implicit integer conversion rules as things that you have done differently today. What should be done to avoid such premature decisions in the programming language design?
So let me first answer your first part of that question. Do I have any recommendations to wannabe language designers? And I think the first recommendation is don't. It's a lot of work and it's usually failing. We have hundreds of languages being designed every year and hundreds failing. Designing a new language sounds sort of glamorous, and it is if you succeed, but it's probably easier to become a basketball star. One of the reasons is that you need a really solid reason to make a new language. The old languages are quite often quite mature and quite effective at what they're doing. And so if you have new ideas, you'll find that the older languages tend to absorb them, either as features or as libraries. It's a very tough field. Now, what did I learn? Some things I learned from the beginning, which was that you had to evolve, you had to gradually grow, not too fast, as guided by real world use and feedback. That's an important thing, and there's quite a few people that don't quite see that yet because they think it's like math and you just solve it, have the proof. If I was going to do things again, I would have fought harder against the implicit conversions, of course. But hey, I was a brand new researcher, and very senior people said that was essential to have those conversions, and I would have been out of business if I had tried to fight this. I'm very keen on static, of a good static type system. And then I'm going to drift away from language technical issues. If you go back to the design and evolution of C++, there's a set of rules of thumb, design principles, and you'll notice that 3/4 of them are social. They're not language technical, they are about what you're trying to achieve and how you're trying to achieve it. And I would definitely want to articulate the both the overall aims, what is the language for, and the language technical aims, what are the fundamental techniques in the language. In C++, it was classes with constructors and destructors, and the aim of building types, user-defined types, that was just as good as the built-in ones. One thing I didn't do right, and I don't know if I could have done right, but certainly it's hurting us these days, is we didn't have a good governance model. That is, I think good language has to be controlled by a small group of people. Good languages comes from individuals or small groups of people, not from large committees. And we now have a large committee, 400 people, 200 people, 50 people turning up, and we have to have agreements there. And you have voting on everything. And I think we need more guidance. We needed a secretariat of full-time people working on the language evolution. And we never had that, and that's a problem. It makes things very much more difficult. We have all the energy, all the enthusiasm, but it's really hard for people to challenge all the other people that are enthusiastic into something that can be done and be consistent, coherent direction.
I understand. Thank you very much for sharing your thoughts on this one.
Okay, another question. A lot of C++ programmers report that the latest features of C++ aren't adapted to the projects they currently work on. How can the adaptation of the newly added features be increased in ongoing industry projects?
Now, any language that survives for decades or a few decades will have the problem that there's code written a decade ago. And it's hard to fit new stuff into it, to fit it with the old stuff. And that's a major problem. I can't just give one rule for how to do that. What I usually look at first is to encapsulate some of the old stuff. Don't let bad interfaces percolate throughout your code. Even if that is what you have when you start, when you do new code, don't let the interfaces interfere all the time. So we have a lot of code out there that uses pointers all over the place in an undisciplined manner. We need to hide that behind interfaces. One of the uses of encapsulation is exactly to encapsulate things that you're not too keen on seeing, things that are ugly, not up to standard. The other thing is that you can't, on average, just try and use all the new features and all the new techniques, because quite often they haven't been thoroughly tested, they haven't been thoroughly tried out. And I'm talking about things used by thousands or tens of thousands of people because they're fashionable. There's also the tool support can be missing and such. So I do a lot of work and experiments with with really brand new things. But I would deploy them till I was really certain that I tried them out well enough. And quite often I find that I need to work a bit harder. There has to be some facilities and the language that has to be changed a little bit, uh, adapted, adopted for newer things. And there has to be a bit more library support before this is useful at scale. We can't expect every programmer to be up on the latest. And we can't expect every programmer to understand the latest techniques. It takes time. And so you have to distinguish between the experiments and the exploratory work and the production work to be done and deployed by the tens of millions of copies and done by hundreds of thousands of programmers. Those are two different things. And for the second one, you also have to get the tools in place. You're not writing your code in just a programming language. You're writing it in a tool chain, including a compiler, and with a set of techniques that depends on a community, talks, videos, books, articles, and such. We live in a community.
Yeah, thank you very much for sharing your thoughts. So my next question is about a removed feature that may have been done differently. So in C++, we currently do not have a way to indicate that a function throws certain types of exceptions in the function declaration. So the need for exception handling when calling certain functions is not directly visible to the programmer. So what may be a good way for such functions to communicate their throwing nature to the callers without auxiliary documentation or exposing their implementations?
I actually think that what we have now is correct and the best. You do not know what exceptional things will happen. If you want to write that in the code, your systems get very, very rigid and you have to recompile a lot. And you get something like in Java where you get a lot of try blocks which are useless. They just say, oh, there might be something happening, let me pass it on, which is the default. You do not know if there's a hardware problem below. You do not know if your memory ran out. And of course, you may still be able to recover because it may simply run out because you asked for a chunk that was too big, even though there's enough memory. Could have been a programming bug. And you don't know if there's a network in between you and the database or a user. So, and you do not know what that network is. So you don't know what those network errors might be. So you have two choices. You can either say nothing, or you can say, we'll take an arbitrary, we'll take a very special exception that can pass through without you saying anything. Or a general exception that is everything that you then have to percolate all the time.
Yes.
Those are, that something like that is necessary because you do not know what errors happens. And so I think we can just as well say nothing because we know that some errors might come along that we have never heard of, rather than pretending we know. And that was the original design. Exceptions are for things that percolate. Exceptions are for things that are exceptional, rarely happens. Exceptions are for things that don't happen very often. That's what they're for. If you use them for something else, and if you litter your code with try blocks, you've done something wrong. Now, that was the original design. That's what we've got today. In the C++ 11 standards, there was a 1798 standards, there was a major push by some people that really wanted to be able to say what exceptions were being thrown. And they managed to get it in, and then they left to build Java. And after a few years, we found that they couldn't be used well. Those exception specifications just didn't work. They didn't fit the model for what exceptions were for. And we took them out again. And I think that was very much the right decision. The wrong decision was to put them in the first place.
So, yeah, first of all, thank you for your explanations. I completely agree that the Java way of enforcing the declaring all the throwable exceptions in the function body is the wrong way. But we can say that actually the programmer is responsible for what to catch and what to not catch. The programmer can decide that a certain function call is not going to throw the exception it says it's going to throw. So it should be the decision of the programmer to not handle that. That's correct. But we can at least enforce, can we at least enforce the exceptions that are explicitly and directly thrown in the function body, that is like thrown using the throw statement to be in the function declaration?
That's what try blocks are for. Sorry.
Yeah, it's okay. That way, throwing calls in the body that are not enclosed within try-catch blocks may be ignored, because we can say that it's the caller's responsibility to decide to whether handle or not. But it also enables us to actually enforces us to communicate our throwing nature to the callees. It is not really the way the Java works, not really what explicit throw, the dynamic exception specification mechanism was before. This is some different approach. And what do you think about this one?
I think fundamentally you do not know what exceptions come. People litter their code these days with no except, and they are quite often wrong. And when that happens, they get a termination. There's some programs that simply cannot afford to terminate. And so that is bad. If you know about an exception, or if you want to handle all exceptions, wrap it in a try block. That's what try blocks are for. And if you have too many try blocks, your code is bad. Because then you are trying to handle things you don't really understand all over the place. Anything you try to handle all over the place is a sign you don't understand what is really going on. And of course, there's costs involved. Try blocks are a very bad substitute for an if then else statement if you know what you're doing.
Yes.
Sometimes my students ask me, Necati, I caught an exception, what should I do? And I say, if you don't know what to do, if you catch an exception, you shouldn't have got it at all.
Exactly.
Another question. We have already worked on C++ 20 and started building C++ 23 and talking about C++ 26. And yet, we still don't have a compiler that fully implements C++ 20. What do you think about the incomplete implementations of the latest standard by the most popular compiler vendors?
Well, we're pretty close with the Microsoft compiler, and the others are coming along. We're not as good as we were with 17, and the reason is called COVID. That has delayed a lot of things. I think it's a slightly unfair question because we're pretty close.
Okay. Keith?
And of course we are talking, and by the way, of course, we're talking about 23 and 26, or even thinking about 29. That is part of the evolutionary model and the feedback model and all of that. We have to be working, thinking ahead.
Okay.
So by the way, we're closing the we actually went past the one hour mark. It's okay for us. We have a lot of time for you, but please let us know when you want to leave or.
Give me, let's say another 10 minutes, 2-3
Okay.
questions, something like that.
Okay, sure. So I want to ask this question. So what do you think about the C++ language as an intermediate representation, given how well it can be optimized? It's almost indistinguishable from directly creating LLVM IR in terms of performance, if written correctly. So can it be useful to create compilers that generate possibly readable C++ code for simple and domain-specific languages that aim for domain experts who are not programmers? Or is it always better for C++ programmers to translate business requirements into C++ directly?
Now, there's a lot of questions here, but I don't think I would like to use C++ itself as an intermediate representation. It is textual, it has all kinds of scope rules. No, we can do better. And the reason I know we can do better is that together with Gabidos Reis, I built an IR internal representation, which creatively is called IPR, internal program representation. I don't call it an AST because it's not abstract, it's not syntax, and it's not a tree. It's a graph representing the program. It's compact for an analyzed program, and it is fast to traverse. And that is actually, I think, roughly the right way of having an intermediate representation. And if I could have a magic wand and sort of perform a miracle, I would make it into a standard that all compilers could read and write. And that would help a lot in the tool building of around C++ because we could do much better with much better tools, and we could build much better tools. And as a proof of concept, the module system in the Microsoft compiler, which is done by Gabidos Reis mostly, relies on something like that, so we know it works. And so, yes, I would love to see that. I've been working for that in the context of static analysis for a very long time, meaning decades. And by the way, this is open source. Look at GitHub for Gabriel.Reis and IPR. And there's also a binary representation of it, which last time I heard of it was called IFC, also available open source. That's the place to look.
Yeah, thank you very much.
Okay, another question. Do you think the committee-driven process is working well for the standardization of C++? What are some main advantages and disadvantages of committee-driven standardization?
I think I mostly answered this question already. It is a big problem and a big advantage. Lots and lots of people coming in with ideas, and it's very hard to coordinate and direct this. Having a committee means that it's harder for people to create dialects and corporations to take over the language and things like that. So it adds to stability, but it adds to the problems of creating direction. It would be There are other models that could be thought of as being better, but they're very hard to get. People have a voting strength; they can vote today. Any of you could pay, I think, $1,850 a year, go to meetings. At the third meeting, you can vote, and your voting strength equals anybody's. And that makes it hard to direct.
Okay, Dokan.
Let me ask another question for you. My other question is about avoiding trivial getters and setters. It's in the software engineering realm, defining trivial getters and setters is said to be verbose and not recommended, but it may be necessary to control access to data members. So do you think it is meaningful to introduce a new syntax for qualifiers of class members, like const but public, to indicate that a particular member is read-only from outside the class but modifiable within the class, without creating different types of getters for it?
It's a very old idea, and I've rejected it several times on the grounds that, yeah, it can be done. It's yet another expert-only feature. It's yet another thing to remember, and it is not worth it. When you encapsulate something, it is very rare. It is not rare to have a single function or two functions that are sort of plain getters and setters. But if you have a whole class that is nothing but getters and setters, you've done something wrong, because that means there's no invariant on the class. So what you should say is, what is a class invariant? What is it that's true after the constructor has run? And then design functions that maintain that. And if you don't need the functions there, and if they don't have fairly obvious names, what you have is a data structure that is not actually a proper class object with an invariant. And then just use it as data.
I see. I understand your point. Thank you very much for sharing your thoughts.
There's lots of little features that can help in some case. And that is a real problem, because if we said yes to all of them just because they were good for somebody and for some things, my overly thick books would be twice as thick.
Bjarne, on page 207 of the Design and Evolution of C++, your book, you say, within C++, there is a much smaller and cleaner language struggling to get out. After some years, after all editions, do you think it finally managed to get out? Maybe it's not much smaller, but a cleaner language. Can we say a cleaner language got out from it?
Everybody and his granduncle think he or she has designed this smaller and better language, but it turns out to be a rather hard thing to do. So I haven't seen it yet. I'm very tempted every year or two to build this language, but then I realized I would have to spend 10 or 20 years working on it, and it's far valuable to the community if I do a tiny little bit to C++ itself than to wait 10 years before there's something new. And no, yes and no. If you look at something like templates with concepts, you have actually something where you can write much better code. You don't need all of that enabling stuff and such. It goes away. Similarly, there are several places where you can actually write code that is much simpler and smaller, not a factor of 10, significant. And so you need, we're back to the beginning again. We need the guidelines to say how to do it. And the work on that is the core guidelines, at least my work on that. So you need the language. It has to be stable. It has to be large. And then you have the guidelines that guide people towards that smaller language. And if you look at the core guidelines and read them, they're not small. But what you actually can end up writing, if you take the guidance from the static analysis that says, no, don't go there, go there, then you are into a smaller language. Again, not the factor of 10, but factors, not percent.
So should we enforce the core guidelines using static analyzers?
Yes, I think we should. And I think it would be really nice if we eventually get standard support for use of static analysis. I don't believe in building everything into the compiler because I also want fast compiles. We got fast compiles with modules now, but still, I don't want to slow it down with cubic algorithms for analysis or anything like that. So I still think there has to be a distinction between the compiler and the static analysis, even though, of course, a compiler is a static analyzer.
Yes, to some extent, it does certain things that static analyzers do, and doesn't. Some of the popular compilers they also offer certain static analysis features as well. If you enable all the checks, they are basically also static analyzers.
Maybe this would be a nice place to stop. We were talking about good code. We started out with something with static analysis and guidelines and such, and we ended there. So maybe this was a nice little bookend of this talk.
Sure, yeah, that works for us. So then, thank you very much again for coming. It was a very valuable event for us. We learned a lot of things. You have given a lot of very nice insights to us on how to look at C++. So yeah, thank you again for coming. Do you have any final remarks that you want to talk about?
No, I don't think so. Just thank you for inviting me, and I hope
Thank
I
you
made
for
some
your
sense to
time
people.
and for your attention. It was very useful. Thank you.
Yeah, thank you very much.